as this stated here for some people. So I think it's the easiest one of the gas laws, and we can apply it to a gas stoichiometry situation like we saw today with magnesium and hydrochloric acid. So let's see if we can look at the concept. First of all, gases have density. Okay? Liquids also have density. Okay? Every material has density. Some of you saw at the bottom of your container, it looked like something was leaking out the bottom as you put it in the water. Well, that something could have been multiple things. But we know that it has to be more dense than the water in order to be going down. If it was going up, it'd be less dense. Gases are the same way, just like liquids. If the gas is more dense than air, the gas will sink. If the gas is less dense than air, the gas will rise. This is how hot air balloons work, off the density's principle. Right? They just change the density of the gas, and that causes it to rise or to fall. If the density of the air is greater than the density of helium, for example, the helium floats because the air is more dense than the helium. This is true for other gases as well. If the density is different, you will have one rising above the other or falling, depending on what we have. If the density of air is less than the density of CO2, CO2 would sink, carbon dioxide would sink, it would fall in this case. Now, for density calculations, okay, density is defined as mass over volume. If we apply this into PivNert, the pressure times the molar mass divided by R times T gives us the density. M is the mass of the gas in grams. Funky M is the molar mass of the gas. The molar mass of a gaseous substance can be defined by knowing the density, the R, the T, temperature, and the atmospheric pressure of that gas. This here is one way of finding the molar mass of a gas very quickly, given this information. So once you find the density of a gas, you can get the molar mass of a gas. That's one of the correlations, as long as you have temperature and pressure staying constant. So if we had a gas that had 2 liters and contained 4.65 grams, the density of gases are given in grams per liter instead of grams per milliliter, because a gas has about 1,000 times the volume as a liquid, about 1,000 times. Liquid volumes are given in grams per milliliter. Gases are grams per liter. This is why we can look at a liter vessel containing a certain mass of gas. The density of this would be 4.65 over what? 2.10. The pressure is 1 atmosphere, the temperature is 270. So what would be the molar mass of this gas? We use this equation. Molar mass is density RT over P. Calculate the density first and plug it in. Density is M over V. Well, maybe I just want to plug that in here for this. Don't even have to calculate. So you put an M here for D and a V on the bottom. 4.65 over 2.10. 2.21 grams per liter. Plug in the 2.21 grams per liter times R. Wait, why is this 300? Gotta be in Kelvin, very good. And 1 atmosphere. R is 0.0821 liters atmospheres per mole Kelvin.
Is that the gas constant?
That's all the gas constant.
No, we just have to know it.
Yes.
We have to memorize all the gas constants.
I don't think you have to memorize them all. They give you certain ones on your equation sheet. So look at that. I can't remember which one it is now. This one I memorized just because we use it. We'll use it a lot. So if you don't memorize it, eventually you're going to get to the point. Doesn't matter. R works for everything. And we're going to learn a little bit more about, well, how does it work for mixture as well. But R works for everything, which is nice. And if you don't know if it's ideal, you assume it's ideal. So in this case, the molar mass of this gas would be 54.5 grams per mole. Once you have the molar mass, could you try to identify the gas? Absolutely. Okay, it might not be easy because you're like, wait a minute, 54.5, what could that be? Well, these are our gas choices. Don't like a whole lot of those. Maybe F2 or O2, nope. N2, CL2, nope. So it must be some other gas. It is not just an elemental gas. So that's how we could determine a gas if we got the molar mass. It's another step. Now for gas stoichiometry, just like we did with solution stoichiometry, the cool thing about gases is the amount of reactant can be in grams of volume. You convert it to moles. Moles convert from reactants to products, and then to the amount of grams or volume. So just like normal stoichiometry here, we're just using volumes to help us out. Now, if we look here at this, it says, what is the volume of CO2 produced at 37 degrees Celsius in 1 atmosphere? When you have 5.60 grams of glucose are used in this reaction. So you've got 5.6 grams of glucose here. You want to find out the volume of CO2 here. So you first convert the grams to what? Moles, and then moles to moles. And then to go from moles to liters, we have to use what equation? Yeah, Pivnert unless it's at STP. So boom, doesn't say STP, it's 37, that's non-STP. So we would use Pivnert at that step. So those are the steps here. That's how to convert it into moles of carbon dioxide. And once we get it into moles of carbon dioxide, we can then plug it into our PV equals nRT, solving for V. V is nRT over P, and it's 0.187 moles. You just plug in the numbers, making sure temperature is again in Kelvin, don't mess that up, and you're good to go with the volume. Cancel all the units, come on units, there we go, boom. So that's how to do a gas stoichiometry problem. Just like normal stoichiometry, except sometimes you've got to use Pivnert, and that's it. Now, second level of gas stoichiometry. What would be the volume of CO2 produced, 37 degrees Celsius in 1 atmosphere, when 7.64 liters of C2H2 are used up in the reaction? So we've got liters instead of grams here. So what do we have to convert that liters into? Moles. Now, convert that liters into moles, and then we convert moles of this into moles of our product, and then moles into liters again. Now, the interesting thing about this is Avogadro made a hypothesis, and I can't find the beach ball. Oh, lost it. Lost my beach ball. All right, somewhere. I'll just put it somewhere. The beach ball was a hypothesis. It doesn't matter how big it is or small it is, the amount of gas is proportional to the volume. So that means if the temperature and pressure are staying the same, if I have 1 mole of gas taking up 40 liters, and I have another mole of gas taking up 40 liters, it doesn't matter which gas it is, right? It doesn't matter if it's helium or hydrogen or carbon dioxide. It doesn't even matter if it's a mixture of gases. Any temperature or pressure, as long as the temperature and pressure don't change. So, do the pressure and temperature change here? No. So here's a little trick. You got 7.64 liters here. Got 7.64 liters of C2H2. Okay, setting it up. The cool thing about this is if you've got liters of this, what's the relationship between C2H2 and CO2? Okay, it's a 2 to 4 relationship, so 2 of these to 4 of those. The really cool thing is we usually call this a mole ratio. But if moles and volume are proportional, it's now a volume ratio. Dude, you double this number, that's like 15 point, I don't know, 3 something? No, 2 something? I don't know. Yeah, does that work? Let's go 2. Let's see if that works. So one way of doing it is by using Pivnert. Okay, so you plug into Pivnert, you do all your fabulous calculations, you cancel them out, you get your moles of C2H2. Then you convert that into moles of CO2. And then you take your moles of CO2, you plug it back into Pivner. This doesn't take as long as just quick healing. It takes a lot longer. Just so you know. And 15.3 liters. Whoa, wait a minute. Did we get the right answer already? Oh my goodness, isn't that nice? As long as they stay the same. Yeah, as long as they stay the same and they don't change. If they do change, then you get to do all this. Yep. You know, it depends on the person writing it. Some people love this little trick here. It's not a trick, it's just the fact. Because when Avogadro did his hypothesis, he was doing chemical reactions to see the volume of the gases. John Dalton, who said his paper might have been interesting, he was looking at volume of gases. He wasn't looking at amount of material. He wasn't looking at grams. He was looking at all gases. All of chemistry came from analysis of gases first. We're kind of doing it out of order because we've already learned about all the solids and the solutions, and now we're doing gases next. So it's a really cool relationship. I like it a lot more, but if you want to plug and chug, go for it. It's a fun time. It'll always work. It'll always work this way. If they do change, it'll still work this way. Now, our shortcut, here we go. Boom, boom, boom. So there's our shortcut. Now, let's see if we can apply the shortcut to this situation. Okay. What is the volume of oxygen required at STP when 8 moles of C2H2 are used up in the reaction? So you got 8 moles of this. At STP, what do we know about the volume at STP? Yep, 22.4 liters in a mole. So again, we're going from volume to moles to moles to volume. At STP, 22.41 liters is equal to 1 mole. You have 8 moles of C2H2 times 22.41 times the mole ratio, 5 to 2, using our shortcut. And we get 450 liters of oxygen required for this reaction. That's it. So as long as temperature and pressure aren't changing, you can use the shortcut. And this even gives us a shorter shortcut, so to speak, if you have moles. This is 22.41. Then John Dalton, the one we talked about, his law is called the law of partial pressures. This states the total pressure of a gas mixture is the sum of the pressures that each gas would exert if it was alone. So if you had each gas alone, they would have a certain pressure. You put them together, you add up all their pressures, that gives you the total pressure of the mixture of gases. So this is how his law is written out. PA equals P total times XA. Now XA is called the mole ratio. It's the moles of A divided by the moles total. Or mole fraction, I'm sorry. Not mole ratio, mole fraction. PA is the partial pressure of gas A. XA is the mole fraction of gas A. So if you want to know the pressure of a single gas in a mixture, you take the total times the fraction. And if you have a bunch of gases, obviously, the pressure total equals the sum of all the partial pressures. So if you add up all the pressures due to each one, that equals the total. Okay? Now, the reason I say this is so simple is, well, if you want the total, all the gases that are in there, you add up all their moles. Moles of A, moles of B, moles of C, moles of so on. That equals moles total. And moles and pressure, are they proportional? Yeah, if you increase the moles, you increase the pressure and vice versa. So that's why the pressure, Dalton's law of partial pressure, is slightly obvious, but that's okay. This formula here is the one that people don't usually use, but it gives you an answer to what's the pressure of this gas in the mixture. So how would a problem look in this case? You need volume and temperature to be constant. If you have two different gases, P1 and P2, they each have pressures. When you add them together, the pressure increases. You'll notice here, pressure increases when you combine the two gases together. The volume has to stay the same. So obviously, if you're going to have more particles, the pressure is going to go up if the volume stays the same. Doesn't matter which particles they are. Doesn't matter if it's hydrogen, water, helium, argon, or whatever the case may be. So we'll stop right here for today. Stop right here for today. If you need to make final measurements and clean up, please do that now. Everybody else, please put your goggles away.